G'day guys, and welcome to our lesson on simple circuits. This is an exercise lesson, so we're going to be looking at example questions specifically and assuming that you understand the basic theory about how to find the resistance in a circuit. Now when it comes to problems involving simple circuits, it's a real shame when people lose marks, because there's no need to lose marks in a simple circuit question if you've done enough practice questions like that. This is the type of question that once you've solved, say, 10 of them, and you understand how you solve them, there should be no problem to solve the next 90. So looking at this first circuit I've got drawn here, we have a battery of 10 volts and 3 resistors, one of 10 ohms, one of 40 ohms, and one of 5 ohms. If I forget to write the units, just always assume we're working in volts, amps, and ohms. I'm never going to write a number and assume you understand that's kilo ohms or micro ohms or anything involving the amps and volts. So for each one of these circuits that I draw, this is the first one here, we're going to solve for the total resistance of the circuit, the current flowing through the battery, the voltage across each resistor, and then if we feel like it, the current through each resistor as well. And you can see up here I've written simple circuits, an exercise in total resistance. The reason I've written this, an exercise in total resistance, is because total resistance is generally the first thing you'll try to find out about a circuit. So looking at this first circuit here, first of all, let's find out the total resistance of this circuit. It's immediately a little more difficult than something you'd get in, say, year 10, because this circuit has both a series resistor and then 2 resistors in parallel over here. So it's not either only series or only parallel, it's a combination of them. So although I've said this is a simple circuits exercise, they're more complicated than what you'd receive in year 10. So the first thing we do is reconcile these 2 resistors down to find the total resistance of this part of the circuit here. And the way we do that is we say the resistance across this section here, we'll call this section X. No, that'll confuse things. I'll just leave it. You understand what I mean. Is 1 over 40. So 1 over the resistance of this section is 1 over 40 plus 1 over 5, going by this formula over here. So plugging that into the calculator, we have resistance equals 1 over 40 plus 1 over 5 to the power of negative 1. And that comes to 4.44 ohms. So the resistance of this part of the circuit here is 4.44 ohms. That's another way of saying this circuit here can be modeled as a circuit that looks like this. That 10 ohm does not change. And then instead of drawing these 2 resistors in parallel, from the perspective of the battery, it is as though there is just a single resistor there with a resistance of 4.44. So if that is what the battery is feeling from the perspective of the battery, then we can see the total resistance of this circuit now can be calculated using the series equations, which says the total resistance is equal to 10 ohms from this resistor plus 4.4 ohms. So 10 plus 4.44 ohms, that's 14.44, we'll just do 1 decimal place, ohms. That is the total resistance of the circuit. And I said the total resistance is the first thing we find. The second thing we're going to find is the amount of current flowing through the battery. So we can use Ohm's law. Voltage total is equal to I times R total. Therefore 10 equals I, which is current, times 14.4. I is equal to 10 divided by 14.4, which is equal to 0.69. I have 4. If you're using a better approximation, then you'll have something a little different, 0.694. amps. Because we're working in ohms here and volts, we get amps directly. So the next thing we're going to find is the amount of voltage across each of these resistors here. And the way we're going to do that is, first of all, assuming there is a total of 10 volts available across this circuit. So that means 10 volts has to be dumped across the resistors here and here, or here and here. Let's work out how many volts are across this resistor here. V is equal to IR. So the voltage across this resistor is equal to I, 0.694, times R, which is 10. That's 6.94 volts. 6.94 volts. And then here's the trick. A coulomb of charge coming out of the battery and going around the circuit can lose a total of 10 volts as it goes around the circuit like that. Or it can lose 10 volts going around like that. If it's already lost 6.9 volts across this resistor here, it has, on this resistor or this resistor, 10 take away 6.94 volts, which is equal to 3.06 volts left. So we know the voltage across this resistor and this resistor is going to be 3.06. And this is one of the exercises you do when you get into university physics especially. They say, look at the amount of voltage the charge is given as it passes through the battery, and then trace a single path through the circuit like so. By the time you get back to the battery, you should have lost the amount of voltage that you gained from the battery across all the components that you've passed through. And we can do the same for both paths there. In each case, that it'll lose a total of 10 volts combined across the resistors. Now the final thing we'll do is calculate the amount of current going through each resistor. The amount of current going through this resistor is easy. We knew the amount of current going through the battery, and every charge that goes through the battery has to pass through that resistor there. So the current going through this resistor is equal to 0.694 amps. However, the current going through this resistor will not equal the current going through this resistor here. Because of that 0.694 amps coming through this resistor, you then get a split. Some go there and some go there. If we're talking generally, we assume that more current will go through this resistor than this resistor, because the current finds it easier to go through resistors with low resistance, as opposed to that 40 ohm there. But determining the amount of current that goes through each resistor, we have to refer back to Ohm's law. We know that V equals IR there. So voltage 3.06 is equal to I times R, which is 40. So 3.06 over 40 is equal to I. 3.06 divided by 40. I have that equals to 0.0765 amps. And then we do the same thing for this resistor, V equals IR. Voltage 3.06, we'll skip ahead, divided by the resistance, it was 40 on this one here, it's 5 on this one here, is equal to 0.612. So there's 0.612 amps going through there, and 0.0765 amps going through there. Let's add up the current going through this resistor and this resistor here. So that's 0.0765 plus 0.612. I have that totaling 0.6885. We expected it to be 0.694, but it's less. The reason it's less is not to do with any kind of trick of physics. It's simply that in every step here, we've removed anything beyond the first or second decimal place. in order to approximate. And if we used exact values for all of these, this value here would equal to, well, something very close to 0.694. In fact, this is actually an approximation, but you understand that if we didn't use approximations, the value at the end here would be the same value as here. Let's move on to a second circuit I have drawn in front of me in advance. So I'll try to draw it quite quickly. We've got two resistors here, one resistor here, and then a battery over here. Resistance values are 50 ohms, 30 ohms, and then over here 80 ohms, and we have a battery 20 volts. Let's figure out the voltage across each of these resistors, the current across each of these resistors, the current going through the battery, and the total resistance of the circuit. Four things. First of all, the total resistance of the circuit. Well, we have two resistors in series here, which we can reconcile or model as a single resistor instead. So this circuit is actually, from the battery's perspective, identical to this circuit here. Just two resistors in parallel. This resistor here is the same as here, so 80. And from the battery's perspective, this resistor here would be the combined in series resistance of these two, so that's also 80. So this circuit can be modelled as this circuit here. And so now we've got it down to a simple parallel circuit. We can combine, we can use this formula up here to calculate the resistance of this part of the circuit. 1 over the resistance is equal to 1 on 80 plus 1 on 80. That's 2 on 80, which is equal to 1 on 40. So 1 on R equals 1 on 40. We see that the total resistance of this circuit, which is a model for this circuit, is equal to 40 ohms. So we can remove that and say the total resistance of the circuit is 40 ohms. So just to reiterate what we did there, we combine these two resistors, since they're both in series, into one theoretical resistor, and then we use that theoretical resistor to calculate the total resistance of the circuit by resorting to the parallel total resistance formulae. So the total resistance of this circuit is 40 ohms. Now we can work out the current going through this battery. V equals IR, 20 equals I times 40, I equals 0.5 amps. So the amount of current going through here is 0.5 amps. The current will split off when it goes down here. So keep that in mind for the last part where we calculate the current going through these. But right now we're going to figure out the voltage across each of these resistors. So we use that trick we just explained before. We draw a path coming up from the battery around the circuit. By the time that charge has followed that path, it should have dumped 20 volts across the resistors. That means this resistor, the only resistor that it goes through, must receive 20 volts. However, these resistors over here have to receive a total of 20 volts between them. So we'll figure that out in a second using another method. Let's figure out the amount of current going through this resistor here. Voltage is equal to IR. 20 is equal to I, the mystery current, times 80. So 20 over 80 is equal to 1/4. That is the current there. So the current going through this resistor is 0.25 amps. That's 1/4. We said the current splits. Here's the trick we're going to use. The current splits. So we've got 0.5 coming through here, and then 0.25 goes down there. So the amount of current that took this path here is equal to 0.5 take 0.25, which is equal to 0.25 amps. If there is 0.25 amps going down here, we can use Ohm's law to find the voltage across here. It's 0.25 times 50. That's 12.5 volts. And we said a total of 20 volts has to be dropped across these two resistors. That means there has to be 20 take 12.5 equals 7.5 volts left for this resistor here. Another way of working that out is we'd say this resistor also follows Ohm's law, so the voltage is equal to the current 0.25 times the resistance 0.25 times 30 again equals 7.5 volts. So as you get towards the end of the question, it's like a puzzle in which you've laid down the majority of the pieces. You find there's more than one way of figuring out what the next value is. I hope this exercise helped you understand these circuits. I'm going to do a few more videos solving more and more difficult circuits, and the real trick that they've introduced in exams, I feel in the past few years, is that they'll draw the circuit in a non-orthodox way. So they won't make it neat for you to see where the parallel and the series parts are. It's all a bit of a mess. So the next video will explore a question that challenges you in that way.